Hello, Math 201. Today we end this week with the section 4.5 optimization. And this is probably one of the most useful parts of calculus and something that has real world applications all over the place. And so optimization, yeah, is one of the most useful parts of calculus. And the idea is this: if you're given some function that has multiple inputs, can we optimize the output given a constraint on the input? So the idea is that in order to optimize something means to find the max and min of it. And a constraint is a way for us to turn a function that has multiple inputs into one that just only depends on one. So the idea is, in general, you can't really optimize a function that has multiple inputs in the sense of finding the highest point on it, because it requires a certain, you can't optimize for two variables. We generally have to pick one variable that we can optimize for. And so let me give kind of a warm-up example and talk you through it. And so here's a really silly example, but kind of to give the idea. So given two positive numbers, x and y, whose sum is 20, which values maximize their product? And so this table, before we talk about anything, let's just look at this table. And so here are some examples. So 1 and 19. If you add them, they're 20. Their product is 19. If you do 5.5 and 14.5, again, they add to 20, and their product is now 79.75. 9 and 11 give us 99. 13 times 7 gives us 91. 18 times 2 gives 36. So it seems that the closer these two numbers get, the bigger their product gets. So what is the actual biggest? And so the idea is that because their sum is adding to 20, that's our constraint. If we did not have whose sum is 20, if we didn't have that constraint, we just had given two positive numbers, x and y, which values maximize their product, that wouldn't make any sense, right? Because obviously x could get as big as you want, y could get as big as you want, and you can have as arbitrarily large a product as possible. So this is why the constraint is very important, right? In order to maximize or optimize something, we need to have a constraint. And the thing that we're trying to maximize or optimize is called the objective function. And so those are the two most important pieces in one of these optimization problems. You need a constraint and you need an objective function. And both the constraint and the objective function should be in variables that the problem gives you. And so our constraint is in the variables x and y, which are the numbers, and then our objective function is in x and y. And so we want to use this constraint to maximize this objective function. And so how do we use this to maximize that? The idea is that we put this objective function in terms of just one of the variables by plugging in the constraint. So we'll plug in this constraint for one of the variables, and then we have an objective function in just one variable. Once you have it in one variable, then you just do calculus, right? To find to optimize a single variable function is just to find its max min, which is what we've been doing all this past week. So how do we do that? So take the constraint function, and let's solve for one of the variables. For instance, we can solve for y. So y equals 20 minus x. Plug this sucker right in for y right there. Maybe I'll even put that in red. So plug that guy in for that y right there. So plug in constraint. So plug in constraint. And now we have an objective function in one variable. So this is objective function in one variable. In single variable. And so that's when you know you've done it well. When you have your objective function in a single variable, you're ready to go. Now, how do we optimize this? Well, you take the derivative, set it equal to 0. If you take the derivative of this function, which is 20x minus x squared, it's 20 minus 2x, set it equals 0, you get x equals 10. So x equals 10, we can do the first derivative number line. It's the derivative is positive and then it's negative. So this must be a max. So this is our local max. So x equals 10 is our local max. And so if x equals 10, you plug that in. So y equals 10. So their product has to be 100. And so the largest product is 100, and that's when x is 10 and y is 10. And so that's the idea of an optimization problem. An optimization problem is really just a max min problem where you have a constraint function and an objective function, and you plug in the constraint function into your objective function to get your objective function in a single variable. And so this is what these guidelines say. I won't go over them, but that's the idea. You want to read the problem, draw a picture, super important, identify what the objective function is, identify what the constraint is, use the constraints to eliminate all but one of the variables. And then once you have a single variable, then you do calculus. And then once you have calculus, now you can plug calculus back in to figure out what the variables are. So let's do an example. So let's read the problem carefully. Rancher has 400 feet of fence for constructing a rectangular corral. One side of the corral will be formed by a barn and requires no fence. 3 exterior fences and 2 interior fences partition the corral into 3 rectangular regions as shown. What are the dimensions of the corral that maximize the enclosed area? What is the area of that corral? So we want dimensions that maximize area and the area of the corral. And so we would draw the picture. So this is our exterior fence, 1, 2, 3, 2 interior fences, and they're going to have dimensions. These are all going to have to be the same dimension, X, and then this is dimension Y. And so what's our constraint? The rancher has 400 feet of fence. And so the constraint function in terms of these variables is that 4X plus Y equals 400, right? Because that is the perimeter of fencing, right? We have 4 X's and we have 1 Y, where X and Y are the dimensions of the width and the height accordingly. And then what is our objective function? Objective function. So if that's our constraint, what's our objective function? Our objective function is the area in terms of X and Y. And what is the area in terms of X and Y? It's just X times Y. So we have our constraint. We have our objective function. This is the thing we want to maximize. So we use our constraint and plug it into our area function. So let's do that. So 4X plus Y equals 400. Well, what does that imply? That implies that Y is equal to 400 minus 4X. So now plug in constraint. And what do we get? We get that A in terms of just X is going to be X times 400 minus 4X, which is 400X minus 4X squared. Now we're going to do calculus. Now do calculus to find the max and min. So what does that? It means we take the derivative of our objective function, which is going to be 400 minus 8x, set it equal to 0. And what do we get? We get that x equals 400 divided by 8, which I believe is 5, 50? Yes, 50. 50. So x equals 50. We should double check and make sure that that is a max. And so a double prime of x, we'll do the second derivative test. So second derivative test. We could do the first or the second derivative test, but for practice, let's do the second derivative test. So second derivative test to check it's a max. A double prime of x is -8, which is less than 0. So it's concave down. So it is a max. So it's a max. So x equals 50. If x equals 50, what does y equal? Y equals 400 minus 4 times 50, right? That was what we solved for y. And so y is going to have to equal 200. So y would equal 200. And so that means the area as a function of 50 comma 200 is going to be 50 times 200, which will be 4,000. Wait, no, 10,000. 10,000. So this all in meters, feet. What is this in? Feet. So feet squared. That's the area. And then x is 50 feet. Y is 200 feet. So those are the dimensions, and that's the area. And that's the answer. So pretty straightforward, right? The main kind of new thing to do is to find the constraint and objective function. That's what makes it a word problem. But then doing the actual calculus is what we've always been doing, right? You find the critical points, and you can use either the second derivative test or first derivative test to make sure it's a max or a min. Let's do another example. Suppose an airline policy states that all baggage must be box shaped with a sum of length, width, and height not exceeding 64 inches. What are the dimensions and volume of a square base box with the greatest volume under these conditions? First thing I do is I draw a box. Draw a little box. And because it's a square based box, S, the side lengths are going to be S, and the height is H. And so what is our constraint? The sum of the length, width, and height cannot be greater than 64. And so if we want the greatest volume, let's just make our constraint the biggest that could possibly be. And so our constraint is going to be H plus 2S has to equal 64, right? We're going to work with the biggest amount of box. We should have the biggest amount of length, which is 64. That's our constraint. What is our objective function? Objective. What is our objective? It's going to be the volume, right, as a function of H and S. And what is the volume? It is HS squared. That is the volume of our box. And so we get that H is equal to 64 minus 2S by the constraint. Plug it in. That gives us that the volume as a function of just the side length is 64 minus 2S times S squared, which equals 64S squared minus 2S cubed. This is our objective function that we want to optimize. So let's optimize it. What is the derivative? Well, it's going to be 128S minus 8S squared. Set it equal to 0. You set it equal to 0. We can pull out 128 divided by 2 is 64. So if you divide by 8, what is that going to be? 10, 48, 6, so 16. So if you pull out an 8S, you're left with 16 minus S equals 0. Okay, and so what does that mean? So S is equal to 0 or S is equal to 16. And so why does 0 make no sense? Well, if the side length was 0, then we don't really have a box, right? And so we want S equals 16 to make sure that that is, let's make a number line for V prime of S to make sure that that's actually a max. So let's do the first derivative test. So first derivative test to really make sure it's a max. First derivative test. So we plug in our critical point 0, 16. If you plug in a number less than 0 into this, that will be negative, and then that will be positive, and so it's going to be negative. If you plug in a number between 0 and 16, for instance, 1, that's positive, so it's going to be positive. So negative, positive. And if you plug in a number bigger than 16, that's positive, that will be negative, and so it'll be negative. And so it is actually going to be a max. So this is a max, which is good. It's what we wanted. So S equals 16. What is this? Inches? Inches. Is the max? Is max side length. So then how do we find the height though? So remember the height was equal to 64 minus 2S, which is 16. And so the height will be 32 inches. And so what do we actually want? We want to find what are the dimensions and the volume. So the dimensions, are 16 by 16 by 32 inches. And the volume is just that, all those things times each other, which is, I have no idea what that is. Volume is equal to, I don't know, whatever 16 times 32 is. So 2 times 16 cubed, 2 times 16 cubed inches cubed. So that's the final answer. So those are the dimensions and that's the volume. All right, let's do one last problem. To speed things up, I already wrote out the equations for these ones, but the idea is this. Ladder over a fence. So you have this ladder going over a fence. The fence is 8 feet and the gap between the fence and the house is 3 feet. And we want, what is the length of the shortest ladder that you can put here that will actually hit the house, right? We need to clear the fence and hit the house. And so here's kind of a side view picture of what's going on. We have a side length L. We have this distance X where it hits the ground, and we have this point up here where it hits the house. That's length B, and then this is 3. And we want to optimize L. We want to minimize what L can be. And so this one's a little tricky because we have lots of variables here, but the idea is that this right here is a right triangle. And so we have L squared equals B squared plus this length was X plus 3 squared. And so if we want to optimize L or minimize that length, it's actually easier to optimize L squared. And so instead of minimizing the length of L, we can instead find the minimum of L squared and it'll still be the same thing. And so we're going to use that fact. And so we need to get L as a function of just X. And so how can we get L as a function of just X? Because this is L squared as a function of B and X, right? This distance and this distance. But let's get it just in terms of X, and we're going to use similar triangles. So the idea is that this triangle is the same thing as that triangle. And so using similar triangles, we get that that length over that length is the same as that length over that length. So X over 8 is X plus 3 over B. Solving for B, we get our constraint. That B is, so this is our objective function. So this is the objective. And then this is our constraint. And so B is going to be equal to 8x plus 24 multiplied by 8 and then divided by X. Which maybe actually is easier to write like this. If we carry that, if we divide the X out, it'll actually just be 8 plus 24 over X. That's probably the easiest way to write B. And so that's our constraint. We're going to plug this constraint right here into B right there. And so L squared as a function of just X, what is that going to be? It will be 8 plus 24 over maybe X to the minus 1. Look better. X to the minus 1 times, or plus, sorry, plus X plus 3 squared. So that is our derivative function. Oh, sorry, that needs to be squared. And so let me simplify this a little bit. This will be 64 plus 8 times 24 times 2. What is that going to be? Be 196 times 2. So just for ease of numbers, let me just do that. 8 times 24, whoops, times 8 times 24 times 2 is 384. So 384 x to the minus 1 and then plus 24 squared, which is what, 6. 24 times 24 is 576. Is that right? 24 times 24. That looks weird, but okay. 576 x to the minus 2 plus, and then let's factor this guy out, might as well. This will be x squared plus 6x plus 9. So what do we finally get? Get 73 plus 384 x to the minus 1 plus 576 x to the minus 2 plus, I have a feeling actually this is going to be not the way I want to do it, but because I feel like if I factored this 8 out, that actually might be better. Do I want to do it this way? I think that, I mean, I've already done this, so I'm just going to keep going. But let's just finish it. So plus x squared plus 6x. Okay. That's L squared of x. That's what the length is in terms of x. And now we want to maximize it. So take the derivative. So L squared of x prime, take the derivative. We get negative 384 x to the minus 2 minus 1052 x to the negative 3 plus 2x plus 6, set that equal to 0. Okay, so that's equal to 0. how do we solve for x? I think what would be the easiest way to solve for x here? So yeah, so I'm going to want to divide everything by 2. So I get negative 192x to the negative 2 minus 576. 576x to the negative 3 plus x plus 3 equals 0. And then what I mean, this is actually just super kind of coincidental, but I noticed that this and this both have a 190 or a negative 192 x to the minus 3 in it. Let's see, is that what I want? X to the minus 3. If I pull out an x minus 3, yeah. If I pull an x to the negative 3 out of both of those. So if I pull out a 192 x to the minus 3, what's left over? What's left over is going to be an x, right? Because x times x to the minus 3 gives x to the minus 2. And then over here will be plus 3. Because 3 times negative 192 is negative 576. And so plus 3 and then plus x plus 3. And so I have an x plus 3 sitting here and x plus 3 sitting here. And so I can factor that x plus 3 out. So x plus 3 and then what's left over is negative 192 x to the minus 3 and then plus 1 factor by grouping. So that's, yeah, pretty clever and way harder algebra than I would ever ask you to do. But if you were given this on a homework problem, you could just plug this into a calculator and the calculator could do it for you, sort of like a graphing calculator, but just some algebra tricks. And so then what do we get? We get that, so x to the third equals 192. And so x equals the cube root of 192. So that is what x will get, right? If we set this equal to 0, maybe I should do that. So negative 192 over x cubed plus 1 equals 0. You add the 192 and then multiply. And so that gives us x cubed equals 192. And so x equals the cube root of 192. So that is the x value that will get us that, which I have no idea what that is. So just for kind of our own sake, let's see what 192 cube root is. So it's roughly 5.77 meters. What are we in? Feet? Feet. So that's what the distance x is. And so we want to know what the length is. And so what is, right, assume the vertical wall of the house. What is the length of the shortest ladder? And so we want to know what L is. So L squared of 5.77 is you plug in 5.77 into this equation right here. So copy, paste. And so this will be 24 divided by 5.77. And then this will be 5.77 plus 3, which is 8.77 squared. And so then L of 5.77 is roughly equal to the square root of whatever that is. And so if you plug that into a calculator for kind of posterity's sake, so 24 divided by 5.77 and then plus 8 and then square that, you get 147.85 and then plus 8.77 squared, 76.913, which equals, let's see, oh, I need the square root, sorry, square root of 224.7629, and that is equal to square root 15, 14.99 feet. And so the best ladder has about 15 feet. So 15-foot ladder would get the job done, would clear it. So that's kind of a cool, useful problem. And that should get you through the optimization problems. Again, they're going to be very different because they're all word problems. If you have any questions, please just ask and I'll try and answer them in the Slack. All right, take care.